In this video, you're going to be introduced to the concept of shear stress. So what's a shear stress? To understand what shear stresses are, consider the following example where we have two sheets of wood stacked on top of each other. If you apply two horizontal forces along the horizontal plane of the wood, but in opposite directions, such that force 1 acts on the left of the top sheet and force 2 acts on the right of the bottom sheet, what you expect to happen is that force 1 pushes the top sheet to the right, while force 2 pushes the bottom sheet to the left, so the two sheets slide across each other. This sliding action between the two surfaces is called shearing, and the forces that cause them are called shear forces. So a shear force is a force that makes one surface of a substance move over another parallel surface. In this example, we use two sheets of wood to illustrate shearing, but shearing is typically described for sliding between surfaces internal to a material. The shear stress experienced by the material is proportional to the force acting on it and inversely proportional to the cross-sectional area of the sliding plane, and is given by the formula tau being equal to the force divided by area. The unit for shear stress is the unit of load, or force, divided by area, so it has the SI unit of newtons per square meter. This unit is the same as pressure, so it's also called the Pascal. Another example where shearing occurs is when you use a pair of scissors to cut paper. The paper is cut by forcing two blades onto the surface of the sheet, with the top blade pushing down on the paper while the bottom blade pushes up on the paper. The downward force causes the layer of paper below the top blade downwards, while the upward force causes the layer of paper above the bottom blade upwards. These two layers move in opposite directions and will shear apart, resulting in the paper being cut. Note that the two opposing forces from the scissor blades are not directly aligned with each other, but slightly to the side of each other. If both forces are aligned, then they both push on the same layer, causing the paper to compress instead of shear. This is called compression stress. When the forces are flipped and point outwards from the material, instead of compressing the layer, we end up pulling on it and making it stretch, so the layer is in tension and experiences tensile stress. We see shear forces in many mechanical systems, such as bridges, buildings, and machinery. Their parts are often held together by nuts and bolts. In these examples, the bolts can experience different types of loads and can experience shear stress if there are opposing shear forces. Let's have a look at a particular example. Consider a wooden pole holding up a beam with a single bolt. Under normal conditions, the weight of the beam creates a downward force on the bolt due to gravity. In order to maintain static equilibrium, the beam must exert an equal and opposite force upwards. These two parallel opposing forces create a shear stress within the bolt in the layers adjacent to the plane shown as the dotted line in the diagram. The part of the bolt on the left of the plane experiences an upward force, while the part of the bolt on the right of the plane experiences a downward force, setting up the conditions for shear. If the forces are too great for the bolt to handle, it will shear at this point, leading to a failure of the bolt, like shown here, where the bolt looks like it's been cut. In this example, the shear experienced by the bolt is along a single plane, so it's called a single shear. The shear stress experienced by the bolt at a single shear plane is proportional to the force acting on it and inversely proportional to the cross-sectional area of the bolt, and is given by the formula tau being equal to the force divided by area. Since bolts are cylindrical in shape, the cross-sectional area is circular and is given by the formula pi r squared, where r is the radius of the bolt. As bolt sizes are given in terms of their diameter, we can substitute the radius for diameter, noting that the diameter is twice the radius. So the shear stress equation becomes 4 times the force divided by pi times the diameter squared for the bolt. Let's consider a numerical example. Consider that our beam to be held up has a mass of 10 kilograms and will be connected to our pole using a single M8 bolt. That is, the size or diameter of the bolt is 8 mm in the metric system. So what's the shear stress on the bolt? Using the previously derived formula to calculate shear, we need to know the load or the force and the area of the plane on the bolt that experiences the shear. Since we already know the diameter is 8 mm, we just need to work out the force. Here, the downward force is the weight of the beam, which is equal to its mass multiplied by the acceleration due to gravity. So we can substitute force with mg in the formula. Now we can work out what the shear stress is. Putting the values for mass being 10 kilograms, gravity being 9.8 meters per second squared, and diameter being 8 millimeters or 0.008 meters, the shear comes out to be 1.95 million newtons per square meter, or 1.95 megapascals, where 1 megapascal is equal to 1 million pascals. This might sound like a lot, but bolts and fasteners are typically rated in the hundreds of megapascals, so there's no chance of shear failure here. In summary, shear occurs when two layers within a material slide across each other due to parallel opposing forces acting on those layers. The amount of shear stress experienced is proportional to that force and inversely proportional to the area of the sliding surface. It has the SI unit of newtons per square meter or Pascal.